Welcome back to High Performance Computing, Advanced Scientific Computing. So topic today is lecture 9, and this is the second part of lecture 9 today about accelerators and graphical processing units. In the first part of this lecture, we really thought a little bit about the basics again. So what is the difference between a multi-core CPU with high single-thread performance compared to a many-core chip, which is like an accelerator of thoughts, which basically got the origin from this so-called general purpose graphical processing units, GPUs, which today everybody just calls GPUs, to be honest. And we have seen several different evolutions of this. So starting maybe just from NVIDIA again, you think about Kepler architectures I worked with, and then advancing to Pascal architectures, much more faster, incredible. And then you had even access to Volta GPUs, which makes it even faster and offers already, let's say, very specific tensor core GPU parts and cores, which are, basically then also fueling deep learning on a very order of magnitudes again in terms of training, making it faster. And today we even play with A100, this Ampere architecture. So it is an enormous speed in evolution of GPUs. And of course, here, the challenge we face is how it is supported with GPU libraries, how it is supported for software developers that want to leverage these GPUs, and what are the programming models. We basically here try to really shed the view now a bit less than hardware, but rather thinking about in terms of software and thinking about how I actually program on this speed of evolution. So also because perhaps we see in the future much more heterogeneity. So one of the takeaway messages that in the last 10 years, NVIDIA was dominating the market. So everybody was having CUDA libraries, CUDA-based codes, which are basically optimized for NVIDIA GPUs. And for a good reason. So if you do deep learning based on Nickel and other CUDA libraries and so on, and GPU libraries from NVIDIA, then of course your source is really extremely fast. And however, this led to the fact that GPUs is now a very costly factor on a basically HPC market. If you think about before, it was the interconnect, which I always said in the beginning of the lectures is essentially the most costly factor of a HPC machine today. That is, let's say, the half-truth. The half-truth that comes now is, of course, it's the GPUs. Let's say the summit, right? If you have 6 GPUs per node and then have 1,000 nodes or so, you can imagine that this is a massive price as well. So here, AMD and other, of course, vendors now in the futures have maybe the chance to have a more regulated market, to have a, let's say, and price impact as well. However, from the software perspective, we also have to be realistic and have to think that all the different GPU libraries that we have now, maybe here and there already ported to CUDA, have to be ported also to other GPU models. And that brings us to the topics of this second part of this lecture, where we again reflected a bit how I really would program this now, and basically motivating a little bit the case for you now why I need libraries in this as well. So in one of the earlier lectures, we had already the idea of thinking about how I can now leverage the GPU here, basically very, let's say, straightforward manner. So then basically I have this orange color coding here that you see and all the different colors, which basically represent the mathematical foundation, how you essentially compute, let's say, a matrix vector multiplication here. So a very trivial aspect, but if you go back to some of the deep learning, this matrix multiplication or so, you really have essentially the same idea. So you can break, based on this mathematical models, this complex problem of really do this matrix vector multiplication into essentially these different steps here, where you say, essentially I have a big problem to solve here, but based on the mathematical foundations, I can break it down to extreme similar problems and very trivial problems. The only problem is if you have a big matrix, if you have a big vector, you need a big number of cores to do that in parallel. but that is the exact idea of the GPU, right? So in this sense, you have these ideas of these different steps that you see also represented here, that you take this and break this apart from these different independent computing parts in order to then create the overall new overall part that you see here, to get the results back of this independent computations that you see in the processors working based on the color codes. And in the end, you just the simple, plus will make the addition then to get to the resulting A vector here. I called that here B part and C part in the text, but essentially I think you get the message already through the graphic. And this is essentially the lowest level of how really GPUs affected now the market. So many of the problems we face are actually very trivial, but you have to have, computing in orders of magnitudes of them. And where one of the fields where this is really taking off a lot is basically deep learning. That's why I present another lecture 10. And then also one of my PhD students, Rocco, will present in practical lecture 10.1 some practical insights, how you do really distributed deep learning based on my fundamentals. But then I present here basically in lecture 10, and I give you a sneak preview already, because in the end, you just do signal processing here, and the signal strengthening is already doing very simple ideas of always matrix multiplication, increasing the learning through this matrix multiplications and so on in these different networks. And you see here different structures and also a little bit the idea of the so-called deep learning, which is really fueled by this GPUs today. So in other words, you would say deep learning may not be so popular today if we wouldn't have GPUs, because GPUs are just extremely good to solving that problem. And deep learning is also not a new tactic. So people have invented that before, but at that time, when basically deep learning was more or less invented, there was just simply not the computing that would enable the deep learning that we have today. So in a way, you see, it's a bottom-up versus a top-down problem, so to speak. You want to do great things in science and great things in AI, but then the underlying technology doesn't follow suit. But of course, at some point in time, like we see now in history, so to speak, deep learning is now really fueled by GPUs. So basically the hardware is following suit. Now you can do very nice things with deep learning. And as I said, also in one of the first lectures we had really in the course, if you think about deep learning, don't think about a typical artificial neural network, which has just, let's say, millions here or thousands of these different hidden layers. That's not really the power of deep learning. We see also in the video that I show with you a little bit, again, that deep learning is fueled also by very specific architectures that we will explore a little bit in lecture 10, with convolutional neural networks, for instance, that then are based also on the traditional classification approach of typical shallow artificial neural networks, and then basically the idea how you can classify different digits, for instance, that you see here if you get the 3 into this network. But of course, the details would come in lecture 10. But as a sneak preview, and thinking about all of these connections now, which in a way will be always strengthened with a learning signal in an abstract notation, and meaning a lot of matrix multiplication along the way. And the matter of the connections really is a very crucial part in this. And basically, that's what we will also explore in lecture 10. But of course, here a sneak preview on this, how that looks like. here you see now also the innovation that took place. This basically this convolutional networks a little bit shown here in reviewing lecture 10. So you see it's really now also based on different feature maps. It's not only connections, it's also having different, let's say, feature extraction mechanisms before you do any classification in the networks. And we will talk about this basically in subsequent lectures. We continue here with spiking networks, which are more or less cutting edge research as well, and not so relevant here as part of this lecture. However, basically as a kind of programmer now, the question remains how you would fuel and how you would basically create all of these neural networks we have seen now. And I know for you, many of you, basically it's not obvious, and we will see how that materializes when we talk about lecture 10, of course. What are neural networks? There will be a very simple introduction. I start from zero. And some of you have been maybe in my cloud course there, we have talked about this as well. So there you have some benefits. Taking the cloud course, you will understand this perhaps a bit better. But because there are some small overlaps in the course, of course, thinking about artificial neural networks and deep learning. But essentially, the role of libraries should be not forgotten here, as I was alluding to earlier. And you say that TensorFlow and Keras are just two examples of tools, and you can go on to PyTorch, to MXNet, and so on, that are already basically have a very strong library set for these deep learning algorithms in order to be executed with extraordinary performance on GPUs. And even if GPUs are not available, they're still operating on CPUs. But one of your learning experience of assignment 3 in this particular course here in HPC will be that CPUs are basically a non-go for deep learning. Hence the idea of assignment 3, together with some OpenMP and so on, which you will learn or which you have learned before. The idea is really to learn a little bit what's the difference between many core GPUs and the role and relevance in deep learning. You will see that in order to do deep learning right, you really need the power of GPUs, and you need hopefully more of them. That also will Rocco show you in practical lecture 10.1, because he's one of my PhD students that really scales to 128 and more GPUs at the same time to be used in cutting edge image analysis models in remote sensing, for example. However, it's good for us to understand that TensorFlow and Keras and PyTorch and all of these libraries are there. They actually support CPUs, GPUs, and so you don't have to fight with the low-level details, so to speak, of implementing now CUDA kernels that have to be implemented on a GPU. In other words, it is a high-level library to take advantage and leverage GPUs. Still, we have to understand, of course, also later what CUDA is, what's the problem with it, of being, of course, also a, let's say, vendor-specific way to program accelerators. But still, we have to see that today, running an A100 NVIDIA card with TensorFlow is showing extraordinary performance. And the question remains if we can go there with the same performance really with other accelerators, let's say AMD cards, which we just now have access to. And basically, this is fueled by lots of data, and hence this HBM I was presenting earlier, the memory and the 900 gigabytes per second, basically latency between memory and the GPU cores plays a certain role in this. So in a way, I was also presenting in lecture 1 earlier, it is big data we're talking about. So deep learning is fueled by big data. You need access to lots of data sets in order to really program and have this data sets really used to the most significant degree inside these big models. If you have small data sets, then basically deep learning really don't make sense. And you have here a typical multispectral remote sensing data set that is essentially based on signals you basically acquire from Earth orbiting satellites here. You basically have the land cover that you can basically differentiate in different classes and basically then create deep learning models here based on different patches that they analyze in order to differentiate what basically you have here in terms of multi-labels, or one label even is also possible. And here we have big EarthNet, which is one example of a very big data sets where you really need cutting edge GPUs. And this is what we also will pick up in our lecture 10 and practical lecture 10.1. So in order to do this and to a bit better understand why now deep learning is so much fueled with GPUs and why that makes a difference, is here an example of an architecture which is known as ResNet 50. It's one of the cutting edge deep learning architectures for image recognition, for image analysis, based on the typical principles you have learned already a little bit in parts with a convolutional neural network, but with what we also will basically present you a little bit more in lecture 10. But you see here lots of different connections, and all of these connections mean hell a lot of computing in order to be trained. These connections need to be basically always influenced with new values. So here we talk about influencing these matrices and vectors that we basically exchange here again and again with every training run, with every epoch, we call that. We basically have lots of different runs and so-called batches we will talk about in lecture 10 and practical lecture 10.1. But the key message to take away is essentially that you have lots of parameters of this system that you have to train and that you basically have as a very high computational complexity. We're talking about 25.6 millions, for instance, as an example here for ResNet 50 of trainable parameters, which is nothing else that you have seen as a basic principles of doing matrix vector multiplication or matrix multiplications of sort. A very simple ingredients, but you do this incredibly often in order to really train these parameters. And more details we will reveal then, of course, in our lecture 10, when we basically have understood a little bit more of this. So this is more an appetizer, thinking about where GPUs have perhaps today really the best impact, which is AI models. And of course, the classification of land cover that you see in remote sensing is one of our specialities here at the University of Iceland. We're number 6 in the world in remote sensing, according to some university rankings. But it shows you also the motivation for scaling when you have just one GPU, right? Here, the goal could be, when I have one GPU so busy of training 25.6 millions of this training parameters, why not use multi-GPU setups? And that's exactly where my PhD student will also talk about with you. Distributed training on multi-GPUs is his specialty in his PhD studies. And he is an expert that I will basically invite next week to talk to you about in practical lecture 10.1 to share some insights how really HPC can make a significant difference in AI based on GPU architectures. The way how that looks like roughly, to give you an appetizer of this practical lecture, is really that you have certain epochs where you train a deep learning model. And of course, if you have just one GPU available or one node available, let's call it that, it's one node, and each of the nodes has actually 4 GPUs, right? But the benefit is, of course, we have access to many of those. So basically here we have 56 compute nodes on this particular Joule system here in the specific V100. So it's not even using the Joule's booster right now. And I think Rocco will give you some updates on that. We have here the iterations that you have, and then basically see with more nodes, I add more GPUs. Obviously, I have always 4 GPUs in one node. And when I increase the number of nodes, you get this, what I have introduced the last time, the so-called speed up, right? So the time to solution breaks down significantly. And with 24 nodes, which have each 4 GPUs, I train a model which is basically using 96 GPUs in parallel in order to get the AI system trained. Interestingly enough, and this is also what we will looking into a bit more deeper than in lecture 10 and practical lecture 10.1. This is based on traditional MPI partly, right? If you use Horobot, for instance, it uses distributed training using a typical MPI all reduced to make an average of all the gradients. So the gradients are loaded terms. It means a little bit what we learn from one iteration. And of course, it's not obvious to you. We see how that materializes then in lecture 10. But essentially, we have to always basically exchange the progress in learning, and that's what we basically want to show here. And actually what we use for that is MPI, or reduce between the nodes, while of course the model is trained significantly with the deep learning within a node, and of course within the 4 GPUs per node, but then also being able to communicate across the nodes using MPI. So in a way, you can connect better, hopefully, to one of the previous lectures that, across the nodes, we still have communication to be done, no matter if it's shared memory or, in this particular case, accelerated nodes with GPUs. Here we have the same trouble, so to speak, that the node interconnection needs to be, existing, and you have to have communication, and that's what Horowat does for us with distributed training. So when you look now, then how deep GPUs are learned today, and basically how people are programming it today, obviously we learn that basically the most is compute unified device architecture, short is CUDA. And essentially this is of course derived from the fact that NVIDIA GPUs are the dominant market share of GPUs today. It is more or less, if you want, a subset of C, but of course, given the vendor is very dominant in the market, it is understandable that many of the codes use CUDA in order to accelerate not only actually deep learning that we learned with TensorFlow, PyTorch, and Keras and Horowat and so forth, but also many other libraries in scientific computing. So we talk about established codes really, and molecular dynamics, which is a big field we will talk in the second part of our lecture series, essentially later, where you see here an example. These are very established, let's say, libraries of sorts, AMBER, GROMACS, LAMMPS, and NAMD for molecular dynamics are very established libraries that have been even around before actually ever GPUs were talked about, right? So here we see basically that these libraries are also ported to Corda kernels, and we can expect that probably with all the different, let's say, accelerators coming to light, with AMD, for instance, also some of those will be ported to these architectures, and will also make it possible to really leverage then other architectures. But today, if you look into this, you will see lots of these packages, and you can go on and go on. In geoscience, they have RTM and others. They have basically physics with Chroma. You have engineering codes. All of those have in one way or another done some porting to CUDA GPUs because it's just the dominance of the market right now. And you have a benchmark or the yardstick of the V100 here, which is a Volta architecture of NVIDIA GPUs. And you see that even with a new Ampere architecture, you can beat that with even more performance improvements. And in a way, we can expect that it will be actually even more in the future. However, chances are also that we see that some of those packages will be also ported to non-CUDA architectures, as we would say, in the future. But of course, it will take time. And often you'll see in HPC, from the community perspective, not at all is that clarified who is doing the porting. The financial parts of that are almost always unclear to have, let's say, very traditional codes ported to AMD and other GPUs in the future. So question remains if we can keep the track of really being cutting edge performance when we do all the different vendors, because also there we are relying basically on the lowest level in terms of libraries, while these are basically applications which are more or less high level libraries. You probably will in one way or another face if you go to one of the centers, right? If you go to have a job in the area, you will see ANSYS is very much known in the airline industry. GROMACS for molecular dynamics like NAMD. VARF, we will cover that in one of our Earth Science and Climate Sciences. This is weather research forecast. So they are open foam based simulations that some of you that participated in our HPC workshops have seen the avalanche simulation of Flattery, which was basically based on open foam simulations. And AMBER, and you can go on and go on. You see here 450 plus GPU accelerated applications exist. This is an important part today. So essentially meaning then when you start perhaps with a job after you're studying and having your master and maybe contribute to be a PhD at some point in time, or even if you just do support in one of the centers, you would basically face these codes, and they have been already GPU accelerated in many of those. And always take away the message that, of course, we have a slightly different perspective on GPUs from gaming, because some of the students I know are very involved in gaming using GeForce entertainment games and so on. When we talk about, of course, more on the high performance scale, we often talk about the Tesla series in terms of the GPU series. But in a way, for programmers, it's also not exactly the biggest problem to face. It's just more to think that we have a very dominant way right now how we have GPU accelerated applications. And the question remains, what will happen if you have much more heterogeneous GPUs? And throughout my lecture, you will think now I'm paid from NVIDIA, what I'm not. But it's just so much evidence that NVIDIA is the market share right now and basically dominant in the market. The question remains how my lecture will look like in 5 years from now. And of course, this means also maybe here and there some changes. However, the way how that operates and basically fueling a GPU or a many core system, if you want, and abstract a little bit from the word even of GPUs and say a general accelerator of sorts, would be basically this processing flow where you have step 0 here, if you want, working with GPUs, where you have always this host CPU, which is still the challenge I think all vendors have right now. As I said earlier, Intel has an approach where the host CPU was in a way at the same time a GPU, but this is not today on the market. So you would always say a CPU and the CPU memory is essential in order to fuel the data to basically the many core system, which is accessible via a scheduler. And then you have the interconnect with the different RAM that actually is then connecting all of this different many core system parts. So in other words, you always have to firstly transfer data from the host CPU to the GPU memory, which is considered today as maybe one of the bottlenecks of this programming model, because essentially this RAM has become so fast with HBM and others that the question remains if this, let's say, connection is still, let's say, feasible for a high order of scales. For low order of scales, I think you're relatively okay. For a low number of data sets, you're also okay. But if it's big data, high throughput processing, here we could improve probably in the future. Then, of course, you would also have something like the program. So we didn't talk about that much now. I'm always telling you abstractly something about a kernel that is actually a CUDA kernel often in NVIDIA GPUs that is actually then executing something, because data is not everything. You of course have data to be fueled with as many core systems, and we learned that the high throughput on data is one of the key selling propositions here of these systems. But what should I do with this data? So you need an instruction set to do with the data, which is essentially then the kernel that operates in the same way just on many different types of data with as many cores. Hence, you have to transfer the program also from the host CPU to the scheduler and then actually schedule this with all the different many cores basically on this different, moderate performance cores really. Once you then load this GPU program, you basically have then, of course, all the data set it operates on. So there's a very lively interaction. And of course, you can now understand it motivates why we have this 900 GB per second between the HBM and the GPU cores. So here it's a very lively interconnection happening between, writing the data, working on the data, writing the data, working on the data. But in the end, it's very simple instruction sets. It's not really complex material. It's matrix multiplications, as we have seen with deep learning, matrix multiplications, very simple in math, based on, crushing them down in parallel. Because here we can see that many of those instructions can be really benefiting from the parallelization approach. And once you have done all of this computing of all the data, of course, the data remains in the device memory, right, which is over here. And of course, then the question remains how I get it back to really results and into file systems or so. Then I have to put it back to the CPU memory again, to the host CPU. So you see, we still have always a way that is indicating a little bit from the processing flow, CPU to the GPU, do the acceleration step. And once the acceleration step is done, I am back to the CPU to write it to file, to make further message exchanges between nodes, and then do the same thing again. Whatever it does, what your application is doing, it depends. But still, the host CPU problem or challenge today remains. Now coming to one key example, perhaps, which is known as so-called BLAS. It's a basic linear algebra subroutine package, which by now is basically, I think, a very broad package applied. And there are like around 150 routines really for linear algebra. And I think the sexpy is one that you basically have, which is this particular interesting equation here, that you have a single precision. That's basically the S stands for, and AX, times this Y here and plus Y. But in the end, I think it's a very trivial idea of how you do an equation, right? But the key point to take away is now when you do this CUDA enabled, where this QBLAS is standing for, of course, you can imagine now you can really ship that out on many different GPU cores. And with this, have a very big equation system, solved in basically a very fraction of time, because essentially these are just beautiful again to be executed in parallel, based basically on this plus and the idea how you multiply a constant here in the sense with the x. And the sexpy is part of this, QBLAS routines. There are much of those which are in the specification, which are incredibly often used for scientific application, because scientific and engineering applications in one way or another always take advantage of linear algebra routines, very basic materials, but they connect them to a bigger purpose. And with this, you basically have, with the QBLAS library, for instance, an open source package, which is, also, of course, today promoted by NVIDIA with the CUDA toolkit. And today also is actually going more towards standardization with the OpenASCC toolkit. And we basically will just have here some examples just to thinking about a little bit that GPU programming is a little bit different than the things you have seen before. Not only we always have to think that basically we have this strange thing of not being anymore in one memory space that we had perhaps before. And with distributed memory, we kind of using already another type of memory, but here we are sort within the node, but still cannot access the memory. So because it's the device memory, so everything I do in terms of computing there, I have to copy my data, which means in the source code abstract representation here, I have, of course, to basically copy the data here to the GPU. And before I allocate the GPU memory, of course, you have to also think about this, and especially if you use C and so on. And then basically you call the kind of sexpy on this routine, which then operates on the CUDA space. But before that, you have to actually move the data to GPU space and then getting from GPU space the results back to the host CPU in order to finalize and then maybe dump it to disk or whatever you want to do with the results. It is a very little problem of a, let's say, perfect example how you scale up a very trivial program quickly. Because of course, this BLAS SexPy routine would now benefit heavily from having access via the GPU here in this particular blast routine execution, because there I can really do the same operation nicely parallelized across many cores, and then in a fraction of time come back to my host CPU. And this is essentially what you understand in terms of acceleration. So you would say, I have the trouble of doing the SexPy here, and in order to accelerate it, I take advantage of the GPU that I have available in this core, and would be much better to really do this in a nicely parallel in thousands of GPUs with A100 maybe executed before I start off and actually use a CPU and do it much more slowly. Hence, we also have to talk about how the future will look like. We basically face a little bit the idea of getting towards standardization of programming this. Although, to be frank, we have to say that still doing the low-level optimizations with NVIDIA libraries, to be fair, show the best performance. However, from the developer perspective, of course, the question remains what we can do in order to do a much more standardization approach. And one of the examples here is the OpenMP, which is essentially deriving its idea from the pragma OMP statements that you already know from lecture 6 and actually my practical lecture 6.1. But essentially the idea is very similar. Instead of accelerating it by using shared memory, you accelerate by using, for instance, parallel loops over the GPU. But you also learn that in order to do that, the GPU has no data. So there's a previous step that needs to be done, which is a bit shown here with copy out the data from a certain array of sorts and basically prepare the data set in order then to do this pragma ACC parallel loop. And how it looks like is very similar than OpenMP. If you remember, we had the master thread that always remains, and at some point in time it would fork simple helper threads before it joins to be back on the master thread that always remained in the application. Here you have a very similar idea that the master will basically fork, but not, of course, in the same shared memory space, but in the GPU space. And with this having much more parallel threads available than perhaps shared memory can ever do on a typical OpenMP system, because of course the GPUs are here having thousands of additional processors and additional HBM, as we know from the memory space, which makes, of course, a node more expensive these days. They're having access to an accelerator, but of course it accelerates then subsequently the application much more. So that's one idea of doing, let's say, a more idea of standardization in this area. And it's really a topic which is rather new. It's rather not completely understood how much the impact will be, especially if you now face different vendors. But the key message remains that standardization of sort makes sense, especially if you face maybe a future market of not only NVIDIA, but NVIDIA, AMD, and many other, vendors. So here's another example of this, where you basically run the code, finish the code, and then come back to the host. And you still have the host memory with all of these device transfer of the data. But OpenXC is a promising model. And because many people know already how to do pragma parallelization, and we know that loops, for instance, show a great potential of parallelization, for instance. And you see here, the index is just beautiful again for it, multiplied by constant. This is just beautiful for parallelization again. And of course, there are lots of offs of using an accelerator in this particular case, as you would do in previous times, maybe with a shared memory system. And you see the impact and changes of the GPU vendors. I just want to motivate towards the end of this lecture. Here we see actually AMD Instinct GPUs entering the market, so-called MI100s. We have the first we can take our hands on, so that we learn, how to operate and how we use these systems. Of course, here we have to say, because we have to move away from CUDA there, lots needs to be done in terms of libraries, in terms of packages. And we see here Frontier will be one of the systems in the US adopting this, but also we as Iceland are part of the LUMI consortium, basically among some other countries. And here we have also a GPU partition based essentially on the AMD Instinct GPU series. So although there, Iceland's researchers will have access to the LUMI system via this GPU accelerated AMD system. So we see there's a change in the US, there's a change in Europe of really adopting non-NVIDIA hardware into our supercomputers. And this, of course, basically strengthening again the fact that we have to go to more standardization. You see here another approach, which is the so-called heterogeneous compute interface for portability, a very recent approach from CC or C++ runtime APIs and kernel language that really enables us to write portable codes between AMD and NVIDIA GPUs. There, it's of course a bit pushed, let's say, by the AMD ROC software, as we call it, because of course AMD benefits of being also, ported from NVIDIA away, so to speak, from CUDA to more HIP, and with this also standardized language. And the long story that I cannot present just in a couple of minutes here, because HIP would be, let's say, a whole hour or 2 hours, 3 hours, even if not a day of teaching these days how you would program with it. But you see essentially the commonalities with CUDA, right? It's just a much more standardization approach, but however, it is very similar program to the CUDA before. And you see also this when you compare a little bit here, the warps and essentially the different memory aspects, there's always a mapping going on. And the idea is really to do this. So to help software developers that the HIP kernel language is obviously very similar to CUDA, but also enables us then to perhaps use AMD GPUs much more simpler than being just bound to NVIDIA GPUs. And here's another example of this, where you basically have CUDA malloc, where we said we have to essentially allocate the space for variables in the CUDA space. We have to do the mem copy, so the real copy then of this into this, and then basically do a lot of different things. I don't need to go into more details, but you see essentially HIP is doing a very similar thing, launching the kernel like I would perhaps do here in also the CUDA space. Here it's a little bit more generalized, saying I launch a kernel of a vector addition or whatever it is, your computational problem. And then you basically get it, of course, from the device memory back to the host, as we know we do it in CUDA. All of that is, of course, something which, centers now like Jülich, like Barcelona and Finland, and all the different centers in the world we have in praise, and now basically also under the umbrella of the EuroHPC joint undertaking, which is a new endeavor. They have basically trainings, which we will see probably in the future very soon, going more and more away from NVIDIA and supporting also AMD, the ROC toolkit, the HIP interfaces we learned, the OpenMP, and different approaches. In order to understand a little bit the difference and also perhaps the insights of how a GPU look like, I brought you this video again, also to motivate again that I'm not paid by NVIDIA. So I, in a way, also encourage, of course, this movement to different heterogeneous resource providers.
Today I'm excited to announce the AMD Instinct MI100. It's the world's fastest HPC GPU. It's our first CDNA architecture GPU. Exascale computing is going to give us the ability to realize all the advantages we hear so much about in the AI space, as well as the molecular dynamics research, pharmaceutical, energy research. All of those things will be advanced and move forward with exascale computing. We're really excited to be introducing our first generation AMD CDNA architecture GPU. The CDNA is just purpose-built to do computational math, and that's being realized with a nearly 7x performance improvement in FP16 performance, as well as nearly a 3.5x performance improvement over our prior generations. Tremendous results with this new architecture. The AMD Instinct MI100 is going to be the world's fastest GPU for HPC. It breaks through the 10 teraflop barrier, providing almost 11 teraflops, double precision matrix multiply capability. The MI100 is the device that's on a path to an exascale. It also gives you all the capability you need to do your AI workloads, such as VFloat16 and FP16 low precision math capabilities. Along with MI100, we're bringing out our 4th generation software stack, ROCm 4.0, to support developers on this platform. In that stack, we're going to find all the key elements needed to do your software development, including TensorFlow, PyTorch, the most prevalently used AI frameworks, as well as compilers, OpenMP and our HIP compiler, and all the necessary math libraries for the commonly used applications. In order to make sure the MI100 works flawlessly for your systems and solutions, we've been working closely with our system partners Dell, HPE, Supermicro, and Gigabyte to bring these products to you.
Okay, again, also a disclaimer perhaps here that I'm also not paid by AMD, by the way. But of course, as a professor, we have to ensure a certain ground of neutrality, right? In all of these vendor business, you have actually Cray, who is really an established vendor in HPC since decades, having up and down, of course, in the past, and comparing it maybe with IBM of sorts, but also there are up and downs in the past. And in the end, we have to promote really that technology gets forward, and here or there, competition is a very good way to increase essentially the impact. And with this AMD movement and also then, teaming up with established and key players like Cray, you can imagine that this will have a big influence in the market. And we are looking forward to this being also part of it in Iceland with a Lumi supercomputer, basically. And in a way, I could talk on and on. Accelerators are a big topic, and I think in the future I may teach GPUs as a standalone lecture, but we are not there yet today. So here we stay with the HPC lecture, still having some interesting pointers for you. If you want to know more, GPUs is really, and the accelerators in generally, a topic that will shape your future in HPC much more than it had perhaps in the last couple of decades. So I stop here, and we will continue with some interesting workloads of these GPUs in deep learning and machine learning in the next lecture. So see you then.